what math induction is, this is, what is this, day number 8. So just so you're aware, we've got a review day tomorrow, and we're going to review as well on Wednesday and take the test Thursday. If you have a conflict with that, we can talk on the side and figure something out, okay? Math induction. Here's the point of math induction. It's actually pretty powerful and has given us a number of things that we use on a daily basis. If you can show that something is true for n equals 1, and then you can use this general case to prove it's true for the next term, then what you can do is you can go up the ladder. Right? So if it's true for 1 and it's true for the next term, then that means it's true for what? 2. And then if it's true for 2 and it's true for the next term, then it's true for 3, and then we can just go all the way up the ladder and prove it true for any value n. Okay, so that is math induction. There are 3 steps to it. Hopefully you're keeping up with your paper. We can talk later about that a little bit more. I'm going to skip directly to this slide for now. There's 3 steps. Step 1 is n equals 1. Plug it in, show it's true. The second step is, if you screw up the second step, it's because you're not paying attention at all. All you do is plug in k and assume it's true for that. Okay, so it's like a dummy step. It's like, hey, I'm going to show this general case. Right? And then the third step is where the money is made. However, you can only work on one side of the equation. You'll see what that means in a moment. Okay, so I want to show n cubed plus 2n is a multiple of 3 for all values greater than or equal to 1. Okay, so step 1. Step 1, what am I going to do? Prove true for n equals 1. Let's plug it in. If I plug in a 1, I get 1 cubed plus 2 times 1, and I want to prove that's what? A multiple of 3. Okay, so I'm going to write this out as 3 times, let's say, some value m, where m is a positive integer. All right, I'm just assuming that's a positive whole number. Okay, let's prove that it's true. What's 1 cubed? Well, it's 1. What's 2 times 1? Well, it's 2. Well, is 3 a multiple of 3? Yes. In that case, m equals 1, so check that off your list. Done. Okay, let me scroll back up. I just wanted to make a little more space in case you're writing that down. Step 1 should be, if you have a pulse, you can show it's true. Step number 2, just don't screw it up. Okay, step number 2 is the assumption step. So we assume true for n equals k. Okay, so I want k cubed plus 2k to be equal to some multiple of 3. Let's go, I don't know, let's pick a letter. L. Not in favor of L because it could look like a 1. That's the only reason why, unless you do a capital L. You know what? Just for you, David, we'll do a capital L. Don't confuse that with liters, okay? Oh, gosh, now we're going to confuse it with liters. I'm getting rid of it. David, we're going Q. Q. Q is creepy. Okay. All right, so guess what? I'm done with step 2. I'm done. Step 2 is done. Finished. Okay, so now what am I going to do? I'm going to do step 3. This is the execution step. This is where you either execute the problem or you... Oh, you read my mind. Okay, so we got to prove true. Mark Wahlberg, yes. N equals k plus 1. Okay, so let's do some pluggage and chuggage here. All right. So if I plug in a k plus 1, this is what we would get. And I want to show it's equal to 3 times, let's give another letter here. V, B, that looks like a 6. M is in manly, Mancy, I don't know. Okay, we have to use W because we already used M. For some W in the positive integers. And to be honest with you, I failed you as a teacher. I should have wrote that up here where Q is in the positive integers as well. Okay. Sad children. Mostly talking about myself. Okay. I'm going to pause the video so you can think about this for a moment. Let's make it look like step 2. At least part of it look like step 2. So in step 2 I had k cubed plus 2k. Do I have a 2k? Actually I do. I have a 2k plus 2. Okay, so I see this piece is showing up from step 2. Expansion. K plus 1 cubed. Oh, I can use Pascal's triangle. How about you? Yeah? Okay. So let's think about this for a moment. We'd have 1. What in row 3? It's 1, 3, 3, 1. Okay, let's see what we get. That'd be 1k cubed. That'd be 3k. Squared, yep. That'd be 3k. And that'd be 1. Oops. Okay. Let's drag this over here. And I don't really need that 1 anymore. Okay, so let's do a little work on this now. Do I have what I need from step 2? Yeah, okay. In a moment, I'm going to turn that into what I had above. Okay, but for the time being, I'm going to bring that over like this. K cubed plus 2k. What else do I have? I have 3k squared plus 3k plus what? No, plus 3. Guess what I could factor out of each of those? A 3. Oh, that's a good sign, right? Because I want this to be a multiple of 3. Okay, so what was step 2? What did that equal? 3q. So I have plus 3. I'm going to factor this out. K squared plus 3k. Oops, not plus 3k. Oh, you're an angry individual right now, aren't you? Okay, that's fine. She said do it in the next step. It's just going to look prettier. I'm not going to name her on YouTube because, you never know. She might start getting my... I did, didn't I? So here we go. I didn't use your last name, did I? Did I? Hey, and look at that. What does W equal to? Yeah, W equals this thing. And guess what? That thing is a whole number, right? Because K is an integer. K is a positive integer. We already established that. And so is Q. Q is a positive integer. And so is W. W is a positive integer. Do I need to know what they are? No. But I've proven now that in this case, because I got to write a final therefore statement. Therefore, since this is true, bless you, for n equals 1 and n equals k plus 1, then true for all n greater than or equal to 1 by, I almost forgot the best part, by math induction. Step 1. Austin, while they were trashing your essay, we did math induction. Okay, so step 1, prove true for n equals 1. So 7 to the first plus 2, is that equal to 3 times some number m? Where m is in the positive integers. The answer to that is yes. Is that true? Would m be a whole number? Yeah, m in this case would equal 3, coincidentally. So check that off our list. Let's do the assumption step, where n equals k. So step 2, n equals k. So 7 to the k plus 2 equals, what did we use before q? Oh, Heidi's on it. She's like, q! Use q! If you don't use q, yeah. then something bad's going to happen. Okay, so step 2, I've plugged it in for n equals k. Step 3, execution step. Hopefully you're on the good end of the execution. N equals k plus 1. So 7 to the k plus 1 plus 2 equals 3w for some w in the real numbers, positive integers. Okay, so what the heck? Now what? Okay, so 7 to the first times 7 to the k plus 2 equals 3w. Can I substitute now? No, I can't. I cannot. I cannot, Jenny. If there's 7 to the k's, could I write that there are 6 7 to the k's plus 1 7 to the k plus 2? Is that a legal step? Because there was 7 and I split it up into 7 and or 6 and 1.
FBI would break down.
What is FBI? What is that equal to? 3q. Okay. Oh, this is pleasant. What could I factor out of both of these? A 3. Would this thing right here, would this be an integer? Yeah, because it's just 2 times 7 to some integer. 7 to some integer is an integer. 2 times that is still an integer, plus an integer, positive integer. Oh, well then w would equal 2 times 7 to the k plus q. Therefore, since true for n equals 1 and n equals k plus 1, then true for all n, and that should be all n greater than or equal to 1, by math induction. All right. There are some different types of examples out there. These are what I think are the most challenging. But we can cover questions tomorrow. Or again, I said review tomorrow and the day after. We'll test on Thursday.